Right, so hello everybody, and what we're going to do today is do an hour talking about mathematics, so you better get your mathematical heads on. And then we're going to talk a bit about the assignment, because I think it would be quite good for you to start thinking now about what sorts of subjects might be appropriate. Okay, so we'll have sort of 20 minutes at the end, at least, talking about your assignments in terms of your topics chiefly. Okay, but then there are going to be two workshops after the Wednesday lecture next week and the week after, I think, about poster development and other issues to do with your assignment. Plus there's going to be a dedicated lecture slot when you'll be working with myself and another lecturer in your groups of particular interest. So I should try to put people who are really interested in dyslexia together, and I'll try to put people who are really interested in ADHD. We always have a miscellaneous group, but you know, they can provide moral support to each other as well. And so there'll be a whole lecture slot that you'll have at this time of the day to discuss your concerns and worries about your essay. But I think it's good as soon as possible to start thinking about it. And I know already some of you have done, so that's why it's a good time. Okay, so today we're going to be thinking about mathematics. And this may be a topic that is of particular interest to you. Do we have some people who are particularly interested in mathematics? Put your hands up. Oh, well, you will do. By the end of this lecture, I'm going to have half a dozen people at least. The mathematical brain. So one of the sort of things which I think is most surprising to people who don't know about neuroscience or don't know about the recent research is the fact that we share a very important part of our abilities with number with many other animals. And I'm not even just talking about primates. I'm talking about rodents and you know, pigeons and such things that these tests have been done on. It's a very important issue for all sorts of species when you come to think about it. And in fact, some studies of animals, including studies of lions, for example, have looked at the ability of the creature to be able to judge whether a number is bigger or smaller than another. And it's very important, for example, with lionesses, it's been shown that when they hear the roars of other lions around them, they have to make a decision. And that decision does need to be based on the number of roaring individuals out there they can hear, and they're sort of counting them, and the number of allies they've got in their pride. And so that's actually quite an important calculation in terms of their survival. So in a way, it's not surprising that animals have some sense of quantity. Now, I know that's not mathematics, but you will see by the end of this lecture that actually that is a really important part of how we develop mathematics. And there may be problems with that number sense amongst children who struggle with their mathematics. Okay, so number sense has arisen through evolution. That is not a modern human faculty, but mathematics has not developed through evolution. So we are using parts of our cortex that we would normally have used for other things when we develop our mathematics. And that's also something which is worth bearing in mind when we start talking about dyscalculia, which is the learning disorder associated with number. So just if children have difficulty with their reading, we say they might have dyslexia. If they have a lot of difficulty with their number, then we might say they have dyscalculia. But when we talk about these disorders in that way, it's worth bearing in mind that in both cases, actually, we have not evolved biologically to either read or to do mathematics. So a lot of issues there, really. I don't know if this is going to work. Probably not. Keep it simple, shall we? So evolutionary grounding. So to what extent are our number abilities, especially our approximate abilities, allied to those of other animals? Well, we find that there are certain effects that we observe amongst humans that we share with animals, and one of them is the distance effect. So it can be important to discriminate between two numbers, as with the lionesses when they're deciding whether to attack or not. And what we find is that actually that becomes much easier the greater the distance between the numbers. So, for example, if you're trying to tell the difference between 16 and 60 other lions out there, or you're trying to tell the difference between 16 chocolate drops and 60 chocolate drops, then it really helps if there is a large distance. There is a big numerical difference between those two quantities. Okay, we call that the distance effect. So discriminating between 16 and 60 chocolate bits is much easier than discriminating between 60 and 66 chocolate bits. Now you might think, well, you know, that's obvious, but actually our human abilities to do that, when we have to do it quickly and we cannot count them, are very much aligned to those of chimpanzees, as you can see here. You know, we're better, but we get exactly the same sort of graph forming. So in some of these, I've had to do interpretations of graphs because of copyright issues. But if you look at the paper that's at the bottom, you'll be able to see the original graph. But this is essentially what it shows you: this sweeping decrease in the number of errors that you're making as the distance between the numbers gets bigger. And there's another effect that we also share with animals, which is called the number size effect. So the ability to detect the difference between two numbers, it decreases with the size of the numbers. So, oh, hang on, I think that's actually a mistake, isn't it? The decreases. Oh no, sorry, that's right. So yeah, so it gets more difficult as the numbers get bigger. So we may be trying to discriminate between two numbers, the difference between which is just 2. Okay, so there's just 2 in between 78 and 80. That's the difference between these two numbers. But it's much easier to do that between 6 and 8 than it is between 76 and 78. Okay, so this is called the number size effect. And again, you know, you can measure this in rats when they're going off to try and find lots of chocolate bits, because we assume that they want the bigger pile. And you can see it in humans as well. And you know, interestingly, there's a couple of interesting things about this. I mean, first of all, it follows Weber's law. And Weber's law is about physical intensities. So you can apply Weber's law to your judgment about light intensity, for example. Is this light more bright than this light? And we see very similar curves for light intensity as we do for these sorts of numerical-based problems. So to some extent, you know, number is represented in the brain very similarly in terms of its these approximate tasks as other more physical, sensory tasks. The other interesting thing is, is that actually you see this ability reducing when there is damage to left posterior regions of the brain. I'm not sure, I would have thought you'd probably see it in the right posterior regions of the brain as well, actually. But the reason why we're saying damage to posterior regions of the brain is because, as you'll see in a minute, the parietal lobes appear to be quite important for this approximate ability with number. And when those areas are damaged, then we see these curves sort of beginning to flatten out. And in fact, you know, it becomes much more difficult to discriminate between two numbers, even when they're quite small. Okay, so how is it then that we sort of develop this number sense? You know, when does it arrive? Is it something that we're born with? Well, and how can we know that? Well, one of the ways in which we can do this is with a task involving a novel stimulus with very young infants. So essentially, we know if a young infant can see the difference between this item and that item because they are more likely to lose interest if they think they're the same. So if you replace A with B and they can't tell the difference between A and B, then they will start start looking away. We're talking about like 3-month-old babies, you know, then they'll start sort of looking away. So even when children are very young, you can actually work out whether they can tell the difference between two stimuli. So that's how these sorts of experiments are carried out, simply by whether they appear to get bored and look away, and then we make the assumption that in fact they couldn't tell the difference between those two things. So we see the ability to discriminate ratio developing during childhood, quite early childhood. So even at 6 months, children can discriminate between large numbers, the difference between 16 stars and 32 stars. If the ratio is between 1 to 2 and 2 to 3, so somewhere between 1 to 2 and 2 to 3 is a discriminable ratio that even very young children can pick up and detect. And notice that we're actually talking about quite large numbers here. So this, we talk about this as large approximate numerosity. So they have a sense of number, numerosity, which is working for large numbers. So that could be quite helpful in terms of developing their mathematical abilities. And up to the age of up to numbers of about 3 to 4, they also have an exact awareness. So they can say there's a difference between 1 and 2 and 2 to 3. And that can begin to develop as well. So we see this small exact awareness, and we see this large approximate awareness before they have actually started to learn to formally count. So these are the two tools which children appear to need in order to develop their formal sense of what a number is. So where in the brain do we think this is occurring? Well, one of the ways in which we can find that out is to do an fMRI study. Quite often we look at differences in terms of two conditions using fMRI. But actually, another way of doing it is to do a conjunction analysis where you're saying, well, what are the similarities in brain activity for different conditions in which numbers are coded in different ways? So you can compare the difference in activity when you present numbers in Arabic form with letters and with colours. You can also look at the difference in activity when you present numbers in written form compared with other words. And the interesting thing is whether, in fact, the activity related to representing numbers in that way is the same as representing numbers in that way. So if you find a difference in activity between numbers like this and letters and colours, then it's also the same in the same region as a difference in activity when you present numbers like this and spelt words that are not numbers, then you can be pretty sure that what you're looking at is the neural activity associated with number representation, irrespective of whether it's in Arabic form or whether it is in written form. Because otherwise, what you could be looking at is activity associated with decoding this Arabic form or reading numbers as opposed to, which may not be the same as number representation. So this is why we do these experiments where not only do we look at the difference between numbers and letters and colours and other stimuli, but we actually look for similarities in those differences when you represent numbers in different ways, because then you're just reducing yourself to the brain activity to do with number representation in the brain, irrespective of the way in which the number has been presented to you. So this study was done by Eager in 2003. And I think that if you look at the, I'm not sure, I think it is actually, I have put some sort of form on here. Oh yes, okay, so I've done my own diagram on here, but I think you've got the original diagram on your notes. And what you can see, sorry, this is not the right, let me just, I don't want to blank it out, I'll reverse it. So what you've got on your notes here, oh, you're right. Well done. Sorry, that should be on there. Very good. Otherwise I'll lose it. Thank you, John. So what you should see on your notes are two images like this. Do you remember what sort of slice this is? Okay, you've forgotten it already? What sort of representation of a brain do we call this? What sort of slice? Transverse, yeah, transverse slice. You've also got a coronal slice here, so it's actually going through like that. And this is the back of the brain there. So what we're looking at is activity here and activity there on the parietal lobe. So if you've got your brain in front of you, where are the parietal lobes on that plastic brain? Yep, good, good, good. Touch the parietal lobes. Very good, okay. So irrespective, and you can see you've got some graphs there, and you can see that irrespective of whether it is in visual or auditory form, or whether you're actually hearing the word, or whether you are actually being presented with the number in an Arabic form, numbers, the representation of quantity still seems to be activating that part of the parietal lobes. So it seems likely that the parietal lobes are extremely important for representing quantity. Now, another study, which was done in '99, actually shows that there is a difference in how you represent quantity when you're thinking about it in a formal way, when you're thinking about number in a formal way, compared with when you're thinking about it approximately. So Stan DeHaan did an experiment where he asked people to carry out simple tasks with numbers, and either to do it in an exact way, so they were actually thinking it through, 3 plus 11, that's 14, or it's maybe a little bit more complicated than that, 3 times 7, 2 7s are 14, another 7, that's 21, whatever. So they're actually thinking about it exactly, or they were asked to do it approximately, very quickly, a very quick calculation without actually working it out formally. And what you find is that there's two different sets of regions of the brain associated with this approximate calculation, which we're calling approximate ancient because we see that occurring in animals, and the exact formulation of the answer, which we know has to be culturally transmitted. So this is very much a cultural transmission model of number, because animals can't do that. And if you haven't had math lessons, then, and you've never been taught anything about maths, you will not be able to, or you've never learnt about maths, then you will not be able to do long division. Yeah. So we see, in terms of the approximate ancient approach to numbers, that there are parietal regions activating again. So this is the back of the brain, this is the front of the brain, you see the eye socket there. And we see this region here, that I'll put them in blank, in white. You can see this region here, very important. Okay, again, it's in the parietal lobes. When you're carrying out, this is the back of the brain here, I think. Is that right? When you're carrying out it exactly, however, we see a lot of left regions of the brain activating. Now, why do you think that might be? Why might, and you know enough, I think you know enough now about this to make a hazard a guess as to why the left hemisphere becomes engaged when you're working out mathematics formally. It's a sequence. And so what might you be doing with that sequence? Yeah, not so much reading it, but actually just talking it through in your brain. So when you do long division, I always think, right, I've got to put that in that column. 1 plus 1, that's 1, carry 1, whatever. I'm actually talking and talking it through. So language can be very important for a lot of formal thinking processes. And this is true with mathematics as well. So we have parietal regions involved with making approximate language-independent estimations, including of large quantities. But we have language regions in the left hemisphere particularly activating when we start using our formal mathematics, because we need to think it through step by step and we are actually probably talking to ourselves. There's going to be an inner dialogue there about what we're trying to do. And in particular, they saw activation for approximate estimation of large numbers in the intraparietal sulcus. And because this is often referred to as the IPS, and because if you're interested in number, the intraparietal sulcus is going to come up so much, I think it might be good if you could try and find it on your brains. Okay, the intraparietal sulcus. Have a little look. There's one on both sides. So this is the intraparietal sulcus here. This is the back of the brain, front of the brain. Yes, I think that's it. Yeah, that's it. That's your intraparietal sulcus. Yeah, it's along there basically. Intraparietal sulcus. Yes, a little bit further back, but yeah, I don't usually see that. But you're right. No, that's it. You're right. Don't take your finger off that. I'll lose it. Yeah, it's usually down there. It's where they sort of usually indicate there. Are we all okay with that? That's right. We got it? Yeah, it's there.
Oh, is that what intra means? That it's in the middle, like this way?
Intra, between, yeah. It's between. It's in the parietal. I suppose. I don't know what intra means between.
Okay.
But that's the parietal sulcus. Yeah, I think it means between the inferior and the superior parietal lobule, actually. That's obvious, isn't it? Thinking about it. Yeah, so you've got inferior parietal lobule, superior parietal lobule. Okay. We're okay with that? More or less, not too serious. Okay, so you're probably beginning to guess how this comes about, how you actually learn to count. And if you've ever sort of worked with young children, you've probably been aware of the fact that children can quite quickly appear to count without actually having any sense of the meaning of what they're saying. So, you know, they can learn a song saying 1, 2, 3, 4, 5, 6, 7, but it doesn't actually mean they think that they know how to count, or they can say, oh, there's 6 stars there and 4 stars there. So what we're talking about is counting with meaning, and it's not at all straightforward. It's quite a challenge, but if you've got those basic tools, then you've got your ability to tell the difference exactly between very small numbers, and you've got your ability to tell the difference between very large numbers in an approximate way. Then you have got the basic tools you need. So new maths concepts, in other words, you know, working towards large exact calculations, can be constructed by bringing together 2 initial systems, the large approximate and the small exact system. And this has actually been credited to Spelk and Carey by Mark Johnson. I'm not exactly sure. I mean, it seems to me like quite a step forward when people formulated this understanding, but I've never been able to find the paper that says, we've got a good idea, we think it happens like this, and put it all together. But Mark Johnson, in his book on developmental cognitive neuroscience, credits it to Spelk and Carey. So this is the problem, if you like. We have, this is the sort of thing you could give a child, and you could say, well, you know, can you count up, tell me how many stars there are on each of these cards? And to begin with, a child actually will very easily say, well, there's one here, and then there's sort of many. Actually, so this is the starting point. It seems from year dot almost, children can always know the difference between one and many. You know, it's all just sort of lumped together after that. But we have to be wary here, because what appears to happen straight away is that we have what we call an object file system. So in the object file system, it's kind of like a lexicon of memory, where you put in particular concepts. And it starts off with children being able to say, yeah, there's 3 dogs there. Okay, there's 3 dogs. And you think, oh, great, they can count. They've counted 3 dogs. But actually, that's not the case. Because what they're really doing is being able to identify as a mass that there is some sort of threesomeness going on. But it's actually specific to the dog situation. Okay, and all the 3 dogs is actually all put together. So in the object file system of the child, we have dog, dog, dog. Oh, and there's another dog, dog, dog. Okay, but it's not generalizable. If 3 cats come in, they can't say, oh, there's 3 cats. Okay, because all they've got in their object file system is dog, dog, dog. And anything that matches dog, 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 they can say, oh, yes, there's 3 dogs. But that's not quite the same as having grasped the idea that there is 1 dog 3 times in this group. Okay, that's when you start having a flexible general idea of number. And that's a really useful thing, because you can extend it and transfer it to cats and people and whatever. And in fact, moving from 3 to 4 appears to be a particularly critical sort of point. And it does require some sort of generalization. And what we see is the approximate system playing a role in that. And so what you start off with is children initially being able to map just 1 to the object file system. And they can identify elements between 1 and 4, but not 2 and 4, because 1 and 4 is a big enough ratio to see that there's a difference, right? They're not counting yet, but they know there's a difference. And they can see there's a difference between 1 and 4, but they can't see there's a difference between 2 and 4 stars, let's say, if we think back to that diagram I had on the board. But that's good. Okay, so they've got 1, and they can say there's 1 star, but there's still just many stars. But they know there's a difference between when there's 1 star and 4 stars, but they can't see the difference between 2 and 4 stars. And then children use these systems to be able to identify 2 and 3. Let's say that there is a difference between 2 and 3. There's a detectable ratio difference between 1 and 2 and 2 and 3. And when you can start using your approximate system to identify that there is a difference between these pairings of numbers, then it becomes possible, when it's pointed out to you, that in fact there is some sort of sequence going on here. There is some sort of number sequence that has more meaning than just the sequence in the orders of a song. This is something that can actually be transferred to other situations. So eventually children surmise that each word in the count sequence corresponds to an additional element in the array. And they do that by applying their approximate abilities to see that there's a difference between 3 and 4, 4 and 5. And suddenly they're beginning to be able to actually say, okay, now I understand that what's happening here is that 1 is being added on each occasion. And this is not just specific to dogs. It's not just about putting dog, dog, dog in my memory and being able to see whenever there's this particular configuration, oh, it's 3 dogs. Actually, this is a transferable mathematical concept. So this is a major breakthrough. Neuroimaging studies can also show the time course of learning in terms of brain activity and indicate how the use of the brain changes as a learning task proceeds. So we can actually see this happening in adults as well. And it's important to remember that mathematics is not about, we talked about the intraparietal sulcus, but it's important to remember that this is not where you do all your number processing. Actually, it requires all the brain to be able to do even simple tasks, and certainly in terms of mathematics, as we shall see in a minute. So let's actually have a look at adults learning complex mathematics and see what happens in their brain. Well, what they found, and I'm not sure if, I don't think I've put this diagram on there, no, but I don't think so. But what they found after multiplication training, there was one particular part of the brain, the angular gyrus, that increased its activity when they were now doing complex maths. So they looked at the activity when they were doing maths before training and after training, and what they found was that now they're doing this complex maths, and we're talking about adults here, there is an increase in activity in the angular gyrus. Now this is a part of the brain which is associated with more automatic processing. So that's interesting. So this is not something that you'd even necessarily be aware that you're using. It's something that happens very fast, very, very rapidly. But they showed that there was a decrease in the area here, the good old dorsolateral prefrontal cortex, and you know where that is. By the way, are you able to find the angular gyrus and the dorsolateral prefrontal cortex on that plastic brain? Might be a good thing to do. Touch the angular gyrus if you can. That looks a little bit high. Let me have a look. Might be wrong. Angular gyrus. Yeah, no, I think it's more about sort of, yeah, about there. But you're not bad, not bad. Yeah, angular gyrus. I'm not sure which exactly gyrus it is, but it's around about there. And then, of course, the dorsolateral prefrontal cortex, which is a band of cortex which is going across the front. Yeah, so that's actually a band of cortex going across here. So this is an area that decreased its activation, whereas the angular gyrus back here increases its activation. And what we think is going on here is the dorsolateral prefrontal cortex is about working memory. So when you're learning something new, you're having to step through it. You know, so I wouldn't be, I would be, I mean, it wasn't shown on here, I don't think it was, but I wouldn't have been surprised if you actually saw a reduction in some of that activity to do with language as well. But certainly see a reduction in activity in the dorsolateral prefrontal cortex, because you're no longer having to consciously step through what your teacher has taught you, what you've been told to do. Step 1, step 2, step 3, it's becoming more automatic. So you see a shift. Activity here reduces, activity in the angular gyrus back here increases. From frontal to posterior, as things move from a conscious burden on your working memory to something which is more automatic. So it's important to remember that learning, when we develop a skill, is not about necessarily the brain working harder or working less hard. It's actually about a shift in dynamic networks. We see a shift in brain activity as something becomes learned. And this is true for many different types of learning in the educational sense. Okay, so we've talked about how we develop early on our ability to count, how that gives rise to formal mathematics, which can involve you know, our language abilities, could involve a lot of working memory, a lot of consciously stepping through what our teachers told us once we've got the basics. What can actually go wrong? Why is it the case that there are some children, and indeed some adults, who really have difficulty grasping number? Well, there's many different ways in which we can think about these things, and sometimes, you know, it depends on the perspective that you're coming from. But in actual fact, all of these areas are likely to be relevant. So, first of all, social effects. The values and the beliefs of your society, your family, your peers, your personality, the communication with the teacher, what school you went to, you know, what was the quality like of your teacher. All of those things in terms of what you might call broadly the social environment, we know have an effect on your ability. If it wasn't true, then there'd be no point in sending children to school or worrying about their maths at all, really. There is also an issue of free will. I mean, sometimes people will say, well, you know, this person just doesn't want to get together with their maths. They don't care about their maths. They're not motivated by maths. They don't want to do it. This is actually a very difficult thing to incorporate into our scientific model for reasons which we've discussed before. This idea of free will is very difficult because, you know, often when we're looking at things in a very scientific way, we can reach a point where we think, well, actually, if you go back to the model that I explained right at day one about development, and the idea that we are the product of our environment and our genes, then where do we put free will into that? Because you could say, well, free will is actually, again, about just the social environment, whether you've been with people who have motivated you or whatever, and perhaps some genetic basis to it as well. Perhaps this is not a separate issue. And yet instinctively, I tend to feel that it is. We have to consider it as a separate issue, because otherwise we are ruling autonomy out of the equation. If we rule autonomy out of the equation, how can we say that we are trying to encourage autonomous learners? So either we believe in free will or we don't, it seems to me. And to some extent, that is an act of faith. Do we believe in free will? I don't know. Something we can discuss in issues in neuroscience and education. But certainly motivation of the pupils, motivation of parents and teachers, likely to be an issue. And then, of course, there's the biological. Yes, there is a very significant level of heritability in terms of your maths. We need to look at all types of evidence when we're trying to reach a conclusion about what is causing a mathematical problem. Experiential evidence, the social and the biological. And these issues are likely to be interacting. So there is lots of evidence for non-biological influence. I mean, for example, cross-cultural studies comparing abilities show strong differences depending on what country you're coming from or what school you've been to. But there's also evidence for biological factors. So we know that there are certain disorders such as epilepsy, Fragile X chromosome, Turner syndrome, phenylketonuria. These are very strongly linked to genetic factors, and we know that that can affect mathematical ability. So, you know, it's difficult, it's much more complicated to try to implicate genetics in mathematical outcomes amongst healthy individuals. But, you know, it's clearly possible for genetics to have a major impact on mathematical ability when you look at these particular disorders that are very strongly linked to genes that have been identified as being the culprit. When it comes to people who don't suffer from these quite significant genetic defects, we can see that there is a high level of heritability by looking at all the other factors that explain, and we look at twin studies, for example, and we can see that still that even without these disorders being present, there's a high heritability. However, the genes that are involved are very many, and they are likely to be very interactive. And in fact, we see the same genes involved with many educational abilities in a positive way as in a negative way. So the same candidate genes that we can use to explain disorders such as dyslexia and dyscalculia, we can also see as explaining giftedness in those areas as well. So it's actually about the combination. So it's not the case. It seems unlikely. I can't say it's not the case, but it seems very unlikely that in the future we will be able to say, look, just knock out these genes from the population. This is eugenics, and it's a highly unethical thing and difficult thing to do anyway, so I'm certainly not suggesting it. But even if we decided to do that, it would actually be quite difficult to knock out these genes from the population and say, and therefore we're going to expect our GCSE results to suddenly increase. Because it's the same genes that are contributing to ability as disability quite often, or not disability, but lack of ability, let's say, or low ability in educational outcomes. But with these particular disorders that I've identified here, that's not the case. Actually, there are very specific, small number of limited genetic genes that appear to be responsible. And we can say quite wholeheartedly, yes, that gene has affected mathematical outcomes. So definitely there is a biological influence. How do we think? What do we think in terms of the progress of a child in terms of them developing dyscalculia? What is the sort of trajectory, if you like. Well, the modern idea about this is that there is some sort of core deficit in an inherited foundational capacity for numbers. Inherited in the sense that it has a strong genetic basis to it. A core deficit, foundational capacity, these things are referring very likely to those approximate number abilities that we've been discussing. Okay, and if you think about it, if you don't have those approximate number abilities, so you cannot instinctively, if you like, tell the difference between this number of chocolate chips and those number of chocolate chips without counting them, then you're going to have a difficulty when it comes to understanding the how you count formally, because you have to have some foundational sensory capacity for numbers before you can make sense of the formal approach to mathematical counting and the use of number. So this may be in the detection of numerosity, the ability to code numerosity, you know, how that this is bigger than that pile, very roughly, very approximately. But there's other ideas that it may be the ability to categorize the examples of two-ness together, if you like. So, you know, you've got this, you can tell the difference between this pile and that pile, but you can't then encode that into a category. Okay, so you can see the difference, but you don't know how to represent it or keep it in your mind somehow. So there could be a coding problem as well. When we look at the brains of children and teenagers and adults as well who have difficulty with mathematics, oh, you can't see that very clearly. I think I might have to use, okay, so I think it's supposed to be, oh, no, that wasn't going to work, was it? Okay. This is a glass brain. I think you've actually got an image of this on your notes. So if you look at figures 3 and 4, you will see this a little bit more clearly. So this is from a study by Isaacs, 2001, where they were looking at the calculation difficulties in children who had very low birth weight. And they found that there was a diminution, there was a reduction in grey matter density, and guess where? Parietal lobes. Okay, so again, the parietal lobes, which we know are linked to this ability to make proximate judgments about number, this very foundational, ancient animal sense of number. It's located in the parietal lobes, and children who have, with low birth weight, who have difficulty with number, have a reduction in grey matter in that region, according to this study by Isaacs. So I'm being very careful in how I discuss that, notice, because one of the difficulties is me just saying straight away, oh, you can see from the brain image that this is the problem, this reduction in grey matter. Well, we don't know if it's the cause or the effect. We'll talk a little bit more about cause in a minute, but certainly it's interesting and appears to be part of the picture. There is another study, figure 4, I won't even pronounce that name, produced more recently, that's shown a similar finding amongst teenagers who have difficulty with numbers. Again, reduction in grey matter density in the left IPS, intraparietal sulcus. Okay, so I've redrawn a diagram which is on your notes because this is being broadcast. But it looks pretty much like this, should look exactly like this. Well, it doesn't look like it, but topographically it should be identical. And this was produced by Brian Butterworth in the journal Science. The full reference is on your notes. It's a very helpful coming together of the ideas that we have at the moment about numbers and difficulties with numbers. And one of the things I wanted to point out straight away is notice that Brian has used this brain-mind-behavior sandwich. Okay, so cognitive neuroscience is about linking brain to behavior, but in the middle of that, we need to have mind, we need to have psychology. So it's brain, mind, behavior. And we have genetics. Genetics your genes will produce proteins that produce the structures in the brain. That will influence occipital, parietal, frontal lobes. All of those lobes have been implicated in number function in different ways. And in fact, you know, we've been talking about intraparietal sulcus and angular gyrus, very important for numerosity, representation and manipulation. Frontal cortex, very important for working memory. We were talking about that. So when it comes to developing new concepts and principles, this is going to be very important for that. Yeah. We haven't talked very much about the fusiform gyrus. That is about making, it's a multimodal association area for bringing together inputs such as visual input and also auditory input. So when you're trying to decode numbers that you hear, or you're reading numbers, it's likely to be important. But right down deep in your cognition, we have this numerosity representation and manipulation linked, by the way, to your spatial abilities. And in fact, spatial abilities are a good predictor of your ability in not just maths, but also in science. And interestingly, it's one of those abilities which it can be manipulated by cognitive training. What they haven't done is found that cognitive training can improve your maths, but they have found that they can improve your spatial abilities. Anyway, that's an aside. So we have these fundamental abilities that we've been speaking about, and they support the development of these more conscious, formal ideas such as number symbols, maths facts. Because if I asked you what the square root of 16 is, okay, do you know what the square root of 16 is? 4, right? Well, that's just a fact. I don't believe anybody actually can calculate that, or anybody did calculate it then anyway. I wouldn't know how to calculate it. It's just something you need to know. I suppose you could just go through 1 times 1, 2 times 2, 3 times 3 until you get to something close to it. But generally speaking, you know, maths facts are really important for maths. There are some things you just need to know. But concepts, principles, and procedures, those are also formal, conscious things that we need to develop through our cultural exposure to digits and facts. Yeah? But they're built upon these ancient numerosity abilities. And that allows us to carry out what we see going on in the classroom, which is the behavior. That's the observable bit. We can't see any of that. We can only make inferences about what's going on from the behavior and sometimes from the brain. But we can't see any of this. It's all invisible. But this is what we think's happening. So the top part of the sandwich and the bottom part of the sandwich, you can see. We can see the bottom part now, thanks to the neuroimaging technologies. But these are still abstract theories. The mind itself is an abstract concept. We can't touch it. We just need it. We need that concept to make sense of what's going on. And I always find it strange, really, when people say, why do we need neuroscience to understand learning? Well, you know, if you're trying to work out what's going on here, why would you, if you have the opportunity to tether what you're trying to look at here to not just one observable source of evidence, but another observable source of evidence, why would you not do that? I don't understand. Because actually, if this is not tying in with this, then you know probably down here you've got something wrong eventually. Eventually, this has to tie in with that, just as much as the behavior has to tie in with your ideas about what's going on in the mind. Okay, so that's my interpretation of Brian's diagram. The real one you can find on his paper and in front of you. Are we applying these ideas in education? Yes, we are. These ideas are being applied in education. There's a wonderful study done by Kusian. I'm hoping, I haven't actually got permission to use these diagrams. I hope I'm not going to get into trouble with Nature. But this was the example that I used in my paper in Nature Reviews Neuroscience a couple of weeks ago, because I thought it's such an excellent example of the sorts of neuroscience which really is of interest to teachers. Because in this study, they looked at the brains of children as they were doing a number line task. And number line tasks, we know, are important for developing and applying that sense of numerosity that you have, that relationship between the abstract idea of number and its physical reality. And this was supposed to develop their ability with number to overcome the problems in the dyscalculic group that they had with number. And what you saw was both the children with dyscalculia and the children without dyscalculia improving as a result of using this intervention. And you also see activities, and you see these are reduced activities in the frontal lobes, and you can probably guess why those activities are reducing in the frontal lobes now. It's an increase in the automaticity of what they're doing, isn't it? It's more automatic, so there's less dorsolateral prefrontal cortex involved. But you see the same changes in the brain, or similar, for the children with dyscalculia as you do with the children without dyscalculia. Now there's an important issue there, isn't there? Because when we put this label down and we say, oh, hang on, these children are so many standard deviations from the average, and so now, yeah, we can give you a label of dyslexia or dyscalculia. It's almost, and especially when you can produce brain images that show that there is a difference in their brain activity compared with children who are not labeled in that way, there's a sense that they are really qualitatively different. But actually, that's not the case. And, you know, the idea of labeling somebody as with dyslexia or dyscalculia, it's a sociocultural outcome. Okay, there's nothing in the neuroscience that says that these children are qualitatively different. And you see that both in terms of their behavior, their brain activity, and in their response to interventions which are effective not just for the children with dyscalculia, but the children without dyscalculia as well. So neuroscience, although people very quickly think of neural differences as meaning, oh, there's some fundamental biological, almost medical difference, actually the neuroscience is telling us the exact opposite, that we're all on a continuum. So, you know, we've seen some evidence that people might jump on quickly and say, oh, yes, it's all about parietal lobes. You've got a bit missing there, and that's why you can't do your maths. But actually, you know, the cortex is plastic, and you can produce the same results, probably, from poor teaching. So, you know, we are finding things that are linked to genetic difference, but we have to be very careful. Even just imagine that we did actually find a reduction in grey matter that was very clearly linked to a genetic difference. Would it make it a cause? No, very difficult to say, really, because that cortex is bound to have been influenced by environmental issues, including education. So some of it, yeah, maybe, but not all of it. So I would encourage you to go back to your neuroconstructivist caveats, which I've already introduced to you, and remember, you know, even with possible genes identified, non-genetic environmental factors may still account for large amounts of variance in outcomes. More than half of the variance in dyslexia, according to one study. And if neural pathway construction is influenced by neural inputs from other areas, such as the thalamus, for example, then atypicality in one area here, it might actually be producing atypicality somewhere else. So if you had an atypicality in the thalamus, that would produce atypicality here, because that's mediating the inputs to the cortex. Remember, all the sensory information, apart from smell, goes through the thalamus. So, you know, other atypical parts of the brain may be involved with unusual parietal development. It may be, particularly if it's in a system of the brain, the thalamus is part of one of those subcortical systems, that's going to be particularly more damaging, but more difficult to pick up, just because it's smaller to see, you know. It may be that it's much more difficult to detect. And different types of initial atypicality can result in same outcomes, i.e. if the same brain system can still be affected by different original sources or causes. So please be very careful with this word cause. There are many things we don't know about dyscalculia, but there are many things that we're learning. We don't know what those grey matter differences are actually caused by. We don't know even, you know, whether it's always, I mean, we talk about grey matter differences, but we don't, it's probably going to be synaptic connections, but we don't know that. We don't know when they emerge first in development. Did they arrive in, you know, during education, or was there some evidence of those at birth? And we're only just beginning to learn what sorts of interventions can actually influence mathematical and neural outcomes. So we really shouldn't think about these things as biologically determined. So please beware of cause. As John Morton said, well, this is 2 of his maxims. I think he's got about 10 that he always likes to emphasize whenever he's discussing cause. And he is a he's a developmental cognitive neuroscience. He's written the book, if you like. There is no single cause of anything. Nothing is determined. Okay, it's the sort of thing that a social scientist might say. No, this is the sort of thing that a neuroscientist says. Okay, please be aware of this. And I love this because you could certainly, you hear people say, "Oh, neuroscience is all reductionist, deterministic, positivist. We're trying to reduce everything to numbers and explain everything." Actually, no. What we're discovering is the complexity and the difficulty. And the number of complex interacting causes. Cause is not an easy word. Its popular use would be laughable if it was not so dangerous, informing, as it does, government policy on matters that affect us all. And I get politicians phone me up and say, "Can you say something to me about what causes this, what causes that?" It's always, and it's just not that straightforward. And you put out simple, boiled down messages, and they can be very dangerous. Okay, so that is everything I want to say about that. We have just got 10 minutes left to talk about the assignment. Are there any quick questions on anything we've discussed there? Hello? Somebody said something? No? Okay, I'm going to stop the broadcast. There's no need to do that. That should go onto YouTube.